Brian Maestri back, talking about the assessment of flood risk using HEC-FDA model for coastal evaluations and using the Southwest Coastal Louisiana as a case study. Now I want to talk about Monte Carlo simulation, and we have a little exercise to go through to try to demystify what Monte Carlo simulation is all about. Before getting to that exercise, just want to go back and make sure that where we are right now is we're to the point of calculating expected annual damages. We've talked about stage probability relationships, if you remember those were the engineering input, and then economic inputs, the structure inventory, that included the structure value, the first floor elevation, the depth damage relationships. All that was used to calculate the stage damage relationships. Well, now I notice we got two common things, stages, and so now we get our probability damage relationship, because the stages are associated with a probability and the stages are associated with a damage. So we got a probability damage relationship shown in blue that is calculated in the HEC-FDA model, and then what the model does is it has a formula that we can do in a spreadsheet, but it does it in the model for you. It calculates the expected annual damages. And to show that graphically, we talked about that we just went straight to the stage probability relationships, but usually you have discharge, and then the discharge associated with a probability leads to a stage, and so that lets you relate the stage and the probability. But because this was a coastal situation, we went right there. So there we see our stage probability relationship that was derived, that we already were given. We didn't have to do this step, and it's combined with the stage damage relationship that we talked about using the economic inputs, and both of those then give you what is calculated the damage probability relationship. And the area under that curve, when I first started working for the Corps in 1985, actually there was graph paper, and you took the squares under there and you calculated that area and you came up with your expected annual damages. We've progressed a long way since then. We don't use graph paper to get our expected annual damages. In fact, what we use is we have a formula now in a spreadsheet, and this just shows from the structure detail output part of the model. These are structure records, and then you can see it has the ID number for the structure and the total value of it, first floor elevation, but it shows here the different probabilities and the damages associated with those probabilities. Well, there's a formula down here that you can use, the difference between the probabilities times the average damages between each of these two probabilities. You incrementally add those up, and it gives you your expected annual damages. And that's explained in this formula below. A little beyond this course, but if you wanted to learn how to calculate expected annual damages, it's there for you on this slide. And that is calculated using the probability damage relationship. So when the HEC-FDA model, because we look at a risk assessment course, if you remember, we've been talking about uncertainty surrounding the first floor elevation, the structure value, the depth damage relationships, uncertainties surrounding the stage probability relationship. So all of that is shown by a little probability distribution around all of these inputs. So sometimes when the model, it runs these simulations, and each simulation gives an iteration, and so sometimes it might pick a high ground elevation or a low stage that would lead to higher damages. And so it runs that, so sometimes you get high, sometimes you get low damages, and it works with the probabilities, and you get a distribution. And then the model will take and integrate that distribution and calculate an expected annual damages. The point of this slide is that it incorporates uncertainty. It's not just one number. There's uncertainty that it samples from in order to calculate those values. So now we're to our example, and I wanted to just show you after the values are calculated. As you see here, we're talking about only 16 iterations. We're running this computer simulation. So 16 times it was run. It could have been ran 16,000 times. The following EAD values were generated in millions of dollars. And we'll just put, you have a range of, you have these numbers. They're all EAD values, expected annual damage numbers. There's 16 values. And so what we would do is we would arrange the values from lowest to highest and create a histogram or a bar graph with 6 segments, each equal to $10 million. And we'd define the number of values in each segment and would calculate the mean EAD and the standard deviation. This is what is going on in the model. So if you were doing this, you would sort the value from lowest damage to highest, and that's what we have here. You'd calculate the mean damages from the standard deviation. If my math is right, not always, but if you calculate those damages, the total damages divided by the number of values, you get your mean damages, and we'd just say 28 million if we were using millions of dollars. And you can also, from the 16 values, calculate the standard deviation, which would be $12.8 million. Now, the way the program does is it arranges it into the segments or bins is what it uses. It's based on a range of values. For this example, we said it probably would be based on 0 to 10, 10 to 20, on to 50 to 60, using the lowest and the highest value. You would sketch the values and get its probability of occurrence, and then you could answer some questions. And so, as you see, this looks pretty symmetrical. It looks almost like a normal distribution. So now we're into the risk world. So here's the quiz. Please answer the following questions about the EAD probability distribution. Hint, compare the number of values in a given range to the total number of values, then calculate a percentage. So if someone was to say, what is the probability that damages will be between 41 and $50 million? How would you do that? What is the percent chance that damages will be greater than 40 million? If with project damages are 0, then the EAD values are also the benefits. Now, you're never going to have usually a circumstance like that. There's always going to be with project damages, but I'm just making this simple. If the annual costs are equal to 21.5 million, what are the chances that the VC will be greater than 1 and net benefits will be positive? Well, you can only do this with a single point estimate. You couldn't answer these type of relationships, but you can in the risk world. So moving forward, here's the answers. What is the probability that the damage between 41 and 50 million? Well, if you take this 3 values between 41 and 50 million, when you go back and look at those numbers, and there's 16 total. So that means there's an 18.75% chance, or just round it off, a 19% chance that my damages will be between 41 and $50 million. Now, why is there a range in numbers? Because remember, there was uncertainty surrounding our inputs. Sometimes it sampled high, sometimes it sampled low. It gave you that range of outcomes. And you see, that's what leads to risk. Because of the uncertainty surrounding the inputs, then there's risk because we're not fully certain about our outputs. And that's what we call risk. What is the percent chance that damages will be greater than $40 million? Well, if you look at how many, what's your total number of values? 16. How many values were greater than 40 million? If my math was right, there's 4 values, which means there's a 25% chance that damages will be greater than $40 million. And we had this, if the annual cost is equal to 21.5 million, how many values are greater than 21.5 million? And again, if I did my math right, there were 12 values, which means that there's a 75% chance that the benefits are higher than the cost, right? Because there's 16 values, those are your benefits, relative to the 12 values are your benefits, the 16 in total. So there's a 75% chance that your benefit to cost ratio is greater than 1 and your net benefits are positive. So that's all that really happens, all that mystery behind Monte Carlo simulation. It's really doing simple things like that. Of course, it does it 10,000 times and a large number of numbers, but it's still the same concept. I hope this helped conceptualize, made Monte Carlo simulation more real to you as to what exactly the model is doing.